So we are digging into a massive stack of astrophysical research for today's deep dive. We've got historical analyses of Albert Einstein's original 1916 papers, plus operational blueprints and data logs from the LIGO observatories.
And some of the latest cosmological surveys mapping out binary star systems, right?
Right, exactly. And our mission today is to understand this monumental shift in human history that happened back in September of 2015. To really set the stage for why this specific date is so huge, I want you to think about what it's like to watch a movie.
Specifically, like a silent movie.
Yes, a silent film. I mean, you can follow the plot, you see the sweeping landscapes, you watch the actors' expressions and the explosions.
Can we get the gist of the story?
Yeah, you become incredibly skilled at interpreting the universe of that film purely through the light bouncing off the silver screen. But then, one day you walk into the theater, and for the very first time, someone actually turns on the speakers.
Oh, wow, that's a huge shift.
It is. You actually hear the blast. You feel the bass rumble in your chest. The medium just fundamentally transforms from a visual observation into a completely immersive physical experience.
That analogy perfectly captures humanity's relationship with the cosmos up until 2015.
Really?
Yeah, I mean, for our entire existence as a species, every time we looked up at the night sky, we were essentially watching a silent movie.
Just collecting light.
Exactly. From our naked eyes to the most advanced, massive telescopes ever constructed, we were only ever doing that one single thing, collecting light.
Whether it was like visible light or infrared or X-rays, it was all just different flavors of light.
Right, but in 2015, we didn't just get a clearer picture of the sky. We built an ear to actually hear the universe.
We detected gravitational waves.
We did. And today, we're going to unpack exactly how this discovery happened. We'll demystify a 100-year-old prediction and explore the most violent cosmic collisions imaginable.
And the best part is, we're going to do all of this without you needing a PhD in astrophysics.
Absolutely. So let's start with the foundational concept here. To understand how the universe can create a wave, you first have to understand the medium those waves are traveling through.
Okay, so the ocean they're swimming in, so to speak.
Right, and that requires rewinding about a century to Einstein's theory of general relativity, which, completely rewrote our understanding of gravity.
Because before Einstein, the prevailing view, which goes all the way back to Isaac Newton, was that gravity was this invisible, instantaneous magnetic tether pulling objects across empty space.
Yeah, like a giant invisible string connecting the Earth to the sun.
Right, which works well enough for basic calculations.
It does, but Einstein realized it was fundamentally incomplete. He proposed that space and time are not just this empty, passive theater where events take place.
They aren't separate things.
Exactly. They are woven together into a single, dynamic, four-dimensional fabric known as spacetime.
Spacetime, right.
And what you and I experience as gravity isn't a pull at all. It's simply the bending and curving of that space-time fabric by massive objects.
Now, I remember from high school physics, the classic textbook analogy for this. You imagine space as a stretched-out trampoline, right?
Oh, yeah, the rubber sheet analogy.
Yeah, and if you place a heavy bowling ball in the center, it creates this deep dip.
Right.
And then if you roll a smaller marble nearby, its path just naturally curves inward toward the bowling ball. It's not being magnetically pulled or anything.
Right, it's just following the curve of the fabric itself.
Exactly. But I always felt that analogy was a bit of a cheat because it only explains the space part. It completely ignores the time part of space-time.
Well, yeah, that is the inherent flaw of trying to use a two-dimensional rubber sheet to explain a four-dimensional universe.
It falls a bit short.
It does. A much better way to visualize gravity as geometry is to think about walking on the Earth.
Okay, how so?
Well, if you and I stand at the equator, say, 1,000 miles apart, and we both walk perfectly straight north, our paths start out completely parallel.
Right, we're just walking straight ahead.
But as we keep walking, because the Earth is curved, we eventually bump into each other at the North Pole.
Oh, right. And there was no mysterious magnetic force pulling us together. We just followed straight lines on a curved surface.
Exactly. And when we apply this to time, it gets even more fascinating.
Because massive objects warp the entire fabric, so they also warp time.
Yes. The closer you are to a massive object, the slower time passes for you relative to someone further away.
Wait, really?
Yeah.
Like noticeably slower.
Well, for us, it's tiny, but this isn't just theoretical. The GPS satellites orbiting the Earth right now actually experience time at a slightly faster rate than the phones in our pockets.
Because they're further out from Earth's gravity well.
Right. And if engineers didn't program those satellites to constantly correct for that time warp, GPS navigation would completely fail within a single day.
Wow, that completely shifts the perspective. I mean, when you drop your keys on the kitchen floor, they aren't being magically pulled down by the Earth.
Not at all.
Your keys are just coasting down the geometrical dip that the Earth has made in both space and time.
You've got it. And the sources highlight that this isn't some fringe theory. It's one of the most rigorously tested and confirmed models in the history of science.
Which brings us to the massive problem this creates for physicists.
Yeah.
Because if we accept this premise that reality itself is a flexible, dynamic grid,
It logically follows that grids don't just bend.
they bounce.
Well, if you disturb them violently enough, they shudder.
Oh, they ripple.
Exactly. Einstein realized that if you take immensely heavy objects and accelerate them violently, they should send ripples spreading outward through the fabric of the universe at the speed of light.
Okay, so these are the gravitational waves.
Yes, but these ripples don't just pass through space like a sound wave moving through the air.
What do they do?
They physically stretch and squeeze the space itself as they pass.
Wait, hold on. Let me stop you there because I really want to make sure I'm fully wrapping my head around the mechanics of this.
Sure, go ahead.
If a wave stretches and squeezes the space itself, and we are inside that space,
Yes.
that means it stretches and squeezes everything in it. Like, that means it stretches and squeezes you, the listener, right in your chair, like a momentary invisible funhouse mirror just washing over you.
That is the literal physical reality of a gravitational wave.
That is wild.
It is. As it washes over Earth, the physical distances in one direction momentarily grow a tiny bit longer, while the distances in the perpendicular direction shrink a tiny bit shorter.
And then it just snaps back to normal.
Yep. Space wobbles.
Okay, I have to push back a little on the scale of this, though,
Yeah.
because space is notoriously stiff.
Right? Extremely stiff.
I mean, it takes the entire mass of the Earth just to keep my keys on the floor.
Mhm.
So to make the literal fabric of the universe wobble in a way that we could ever hope to notice from across the cosmos.
Takes a lot of energy.
Yeah, when what could possibly be heavy enough and violent enough to shake the universe like that?
To shake the universe, you need the most extreme, unimaginable engines of destruction in nature.
Okay, like what?
Well, for the waves we've managed to detect, the source is almost always the collision of black holes.
Ah, black holes.
Right. These are the corpses of massive stars that have completely collapsed under their own weight.
And they're super dense, right?
Unbelievably dense. They curve space-time so deeply that not even light can escape their geometry.
They are the ultimate cosmic heavyweights.
Exactly. Now, picture two of these monsters locked in a binary orbit.
Okay, so they're circling each other.
Right, and over millions of years as they orbit, they are actually churning up space-time, bleeding energy out into the cosmos in the form of these waves.
And because they are losing energy, their orbit shrinks.
Yes, they get closer and they spiral faster and faster.
It's the ultimate death spiral.
It really is. In the final fractions of a second before they collide, these two objects, each weighing perhaps 30 times more than our entire sun, are whipping around each other an astonishing 100 times a second.
100 times a second for something that huge.
I know, it's hard to fathom. And when their event horizons finally touch and they merge into a single larger black hole, a portion of their combined mass is converted entirely into raw energy.
Just radiated out as gravitational waves.
Exactly.
The data logs from our sources put numbers on this that frankly defy human comprehension.
They really do.
I read that for a fraction of a second, that final collision radiates more power in the form of gravitational waves than all the shining stars in the entire observable universe combined.
It's true.
I just want the listener to pause and let that sink in. More power output than all the galaxies we can see, shining all at once.
And it is entirely invisible. It is pure, violent shaking of space-time.
That is terrifying and amazing.
It is the most powerful event nature can muster. But here is the great cosmic irony that plagued Einstein.
What's that?
Because these specific cataclysms usually happen more than 1 billion light years away, by the time that universe-shaking ripple travels across the cosmos and reaches Earth, it has faded to an almost impossibly faint tremor.
Oh, so it's practically nothing by the time it gets here.
Right. Einstein himself actually doubted we would ever be able to detect it.
I could see why he doubted it, honestly. Especially because of the fundamental measurement problem we touched on earlier.
The ruler problem.
Yeah, if the wave stretches and squeezes everything, It stretches and squeezes any ruler or measuring instrument we could possibly build.
Exactly.
Like if my ruler stretches by 10% at the exact same time the table I'm measuring stretches by 10%, the table still looks like it's exactly one ruler long.
The change is completely masked.
So how do you measure the invisible when your tools are changing size too?
You abandon physical rulers completely. You have to use something that space-time cannot stretch, which is the speed of light.
Ah, okay.
And this brings us to LIGO, the Laser Interferometer Gravitational Wave Observatory.
LIGO. I've heard of this.
Yes, the brilliance of LIGO is in its design, specifically the mechanism of an interferometer.
How does that work?
It consists of two incredibly long vacuum tunnels, each 4 kilometers in length, arranged perfectly at a right angle to each other.
Kind of like a giant letter L.
Exactly like a giant L. And that shape is deliberate because of how gravitational waves stretch space in one direction while squeezing it in the perpendicular direction.
So if a wave washes over that giant facility, one tunnel is going to momentarily stretch while the perpendicular tunnel compresses.
Spot on. To measure this, scientists split a highly precise laser beam and send half of it down one tunnel and half down the other.
Okay.
At the end of each tunnel is a mirror that bounces the light back to the starting point.
And because the tunnels are perfectly identical in length, the two laser beams return at the exact same moment.
Yes, and the peaks and valleys of their light waves line up perfectly, but in opposite phases, meaning they completely cancel each other out.
Oh, wait. This is exactly how noise-canceling headphones work.
That's a perfect analogy, yeah.
Right, because those headphones listen to the sound wave of, say, an airplane engine, and they produce a sound wave that is exactly inverted,
And when the two waves meet, they destroy each other.
leaving total silence. So LIGO is doing this with light. When the universe is quiet, the lasers cancel each other out, and the detector just sits in total darkness.
That mechanism is the key to the whole machine. Because the moment a gravitational wave passes through the Earth, it stretches one tunnel and squeezes the other.
So suddenly, one laser beam has a slightly longer journey, and the other has a slightly shorter one.
Exactly. They no longer return at the exact same time. They no longer cancel each other out.
And in that tiny mismatch, a flash of light hits the detector.
You got it. That flash is the signal.
Which sounds pretty straightforward in theory, but we really have to talk about the sheer microscopic scale of the measurement happening here.
Oh, it's staggering.
Yeah, because when we say one tunnel gets longer, we aren't talking about inches or even millimeters,
Or
right?
even close.
After traveling 1 billion light years, the wave is so unbelievably faint that the change in the 4-kilometer tunnel's length is thousands of times smaller than the nucleus of a single atom.
It is literally smaller than a proton.
That is insane. The source text actually offers an analogy that puts this in perspective, and I love this.
Let's hear it.
It says it is the equivalent of measuring the distance from Earth to the nearest star, Proxima Centauri.
Which is over 24 trillion miles away, just for the record.
All right, 24 trillion miles away. And being able to detect if that massive distance changed by the width of a single human hair.
It's almost impossible to comprehend. Achieving that level of sensitivity is arguably one of the most fiendishly difficult engineering challenges humanity has ever overcome.
I can imagine.
I mean, to measure a change smaller than a proton, you have to isolate those mirrors from literally everything else in the world.
Right, because any tiny bump would ruin it.
Exactly. They had to account for the vibrations of trucks driving on highways miles and miles away.
Wow.
They had to account for ocean waves crashing on distant coastlines. They even had to cool and stabilize the mirrors to prevent the quantum thermal jitter of the atoms inside the glass from ruining the measurement.
That is serious dedication.
It took decades of relentless effort by a global collaboration of thousands of scientists to filter out all that noise.
And the payoff for all that obsession finally came on September 14, 2015.
Yes, it did.
They had built 2 identical LIGO detectors located thousands of kilometers apart, right?
One in Washington State and one in Louisiana.
And that was to ensure that a localized vibration, like, I don't know, a local earthquake or a truck, wouldn't trick them.
Exactly. If it happens in both places, it's real.
Right.
Yeah.
And on that day, both detectors, separated by thousands of miles of Earth, recorded the exact same microscopic shiver at almost the exact same time.
It was the unmistakable signature of 2 black holes colliding over 1 billion years ago.
A century after he wrote down the equations, Einstein was proven completely right.
It is such a beautiful synthesis of theoretical genius and engineering mastery. But what makes this discovery so vital isn't just ticking off an old prediction on a checklist.
No.
No, it fundamentally transforms our relationship with the cosmos because it gives us a brand new sense.
Like we talked about with the silent movie.
Right. Before 2015, every single astronomical tool we had relied on light.
But black holes, by definition, give off no light.
Exactly. To every telescope we had ever built, a black hole collision was a completely invisible event.
We were utterly blind to it.
We were blind to the most violent events in the universe. But gravitational waves are not light. They are the physical shutter of reality.
So they allow us to perceive events that are shrouded in total darkness.
Yes. That is why astrophysicists say we have gone from only seeing the universe to finally being able to hear it.
And what's wild is that they actually translate these space-time wobbles into an audio file.
They do. It's so cool.
Because these waves have a frequency of vibration. Just like sound waves, scientists can take the laser data and basically run it through a speaker.
Yeah, the frequency of those merging black holes creates a distinct, faint chirp sound.
A chirp?
Yeah, it goes from a low pitch to a high pitch very quickly as the black holes spiral faster and faster right before the final pop of the merger.
That is amazing. You can go online and actually listen to the space-time death cry of two black holes from a billion years ago.
You really can, and that 2015 detection was just opening the door. Since then, the detectors have been upgraded, and we've felt dozens of these cosmic collisions.
Oh, so it wasn't just a one-off.
Not at all. And most importantly, we've detected a completely different kind of event, which is the collision of neutron stars.
Okay, let's define neutron stars because they operate very differently than black holes, and they are really crucial to this story.
They are. A neutron star is the collapsed core of a massive star that went supernova.
But it's not a black hole.
No, unlike a black hole, which is essentially just an extreme warp in empty space, a neutron star is actual physical matter.
Just incredibly dense matter.
Exactly. Gravity has crushed the star so intensely that the electrons and protons have literally merged. It's essentially a city-sized atomic nucleus.
Wow.
It is so incredibly dense that a single teaspoon of neutron star material would weigh billions of tons.
So because they are made of physical matter, when two neutron stars get caught in a death spiral and smash into each other, they don't just warp space.
No, they create a colossal physical explosion.
So there's light involved.
Exactly. They emit a massive burst of light across the entire electromagnetic spectrum while simultaneously sending out powerful gravitational waves.
And in 2017, we actually caught one of these collisions, right?
We did. LIGO felt the gravitational waves shake the Earth, and just seconds later, space telescopes detected a massive burst of gamma rays coming from the exact same region of the sky.
That is so cool. It was like finally getting the picture and the sound at the exact same time in our cosmic movie theater.
It birthed the era of multi-messenger astronomy.
Multi-messenger meaning light and waves.
Right. By having both the physical wave and the light, we solved mysteries that neither sense could answer alone.
Like what?
Well, for example, we learned that the violent collision of neutron stars is the actual cosmic forge where the universe's heavy elements are created.
Oh, like gold and silver.
Yes. The gold in the jewelry you might be wearing right now, the platinum in our electronics, they were all forged in the catastrophic smash-up of neutron stars.
That is unbelievable.
Yeah.
We literally saw the light of gold being created while feeling the physical shock wave of the blast.
Exactly. We observed it happening in real time.
It's incredible. We started this deep dive with a mission to understand how humanity went from seeing the universe to feeling it.
And we've covered a lot of ground.
We really have. We explored how space-time isn't an empty void, but a flexible fabric that bends to create gravity and ripples when it gets violently shaken.
We unpacked the unimaginable energy of merging black holes.
And the mind-boggling engineering required to build lasers capable of measuring a stretch in reality smaller than a proton.
And the craziest part, the field of gravitational wave astronomy is still in its absolute infancy.
Really?
Oh, yeah. We've only just turned the speakers on. But as detectors get more sensitive, the implications become staggering.
What's next then?
Up to this point, we've been talking about detecting waves from dying stars and black holes. But if we can eventually put interferometers in space, which is a project currently in development called LISA, we could theoretically detect gravitational waves that are much older and much lower in frequency.
How old are we talking? Like millions of years?
We could look past the stars entirely.
Wait, what do you mean?
You see, when we use light to look deep into the universe, we hit a wall. We can only see back to about 380,000 years after the Big Bang.
Because before that, the universe was a dense, superheated plasma.
Right. It was opaque. Light literally could not travel through it.
But gravitational waves don't care about plasma.
Exactly. They pass through everything unimpeded. The Big Bang itself, the ultimate violent expansion of space-time, would have unleashed a torrential flood of primordial gravitational waves.
And those waves are still traveling.
Those waves are still washing over us right now. If we can build an ear sensitive enough, we won't just be listening to the death of stars. We could literally hear the exact moment of the universe's birth.
Wow. That is profound thought to end on. I mean, for all of human history, we looked up at the night sky and it looked so serene.
So peaceful.
Yeah, we thought the universe was mostly quiet and still, simply because we only had our eyes open.
But it was never quiet.
No, it wasn't. We have been sitting in the middle of a roaring, chaotic ocean of cosmic collisions since the dawn of time. So next time you step outside and look up at a seemingly quiet night sky, ask yourself, what invisible waves are washing over you right in that very moment, bringing echoes of a billion-year-old storm?